Good day friends. Today we are going to discuss about the challenges with VPLS and how EVPN help us to mitigate or address these challenges. So the challenges with VPLS we are going to address in EVPN based on the route types. So route type 1, 2, 3 and 4 is generally used in the service provider. So above the route type 4, 5 onwards is also there, but generally if you implement the VXLAN or multicast scenario in the service provider or the data center side, so in that case you will use the route type which are 5 and above. But for the service provider, for the basic implementation to replace the VPLS, only we need to learn the route type 4, type 1, type 2, type 3 and type 4. So let's deep dive how these type EVPN route types help us to mitigate those challenges with the VPLS. Multi-homing with the VPLS is little bit difficult, and again in active scenario, active backup is possible, but in the active scenario your whatever bump frame, means you can say that any R frame generated by CE, multi-homing CE will be forwarded by P's to each other, and then that frame will be looped, because generally if we talk about the IP packet it will have TTL. So at each and every hop it will reduce the TTL, and once it's reached the 255 and above, then simply router is going to discard that packet. But the challenges with the frame that we don't have TTL included in that one. So that's the reason if we see on the data center or switching site, we implement this spanning tree to avoid those loops. So in this scenario, if you see that bump traffic is generated by CE1 and PE2 forward it towards the PE1 by attaching the pseudo wire label and the transport label. Once PE1 gets that, he will forward it back to the CE1, because we are working here in the active scenario. So CE1 again will replicate that frame towards the PE1. So if you see that in this multi-homing scenario, in this side there will be so many bump packets replicated, and eventually CPU usage you will go very high, and this end of the network may go down. Second challenge with VPLS is that in the case of multi-homing scenario, if the single homing routers or any remote PE generates any bump traffic, or we can say any ARP packet, so the PE3 will send it towards the PE1 and PE2. So these both router, as they are connected to the CE1, both will forward it to the CE1 routers. So it is unnecessary duplicating the traffic, and unnecessary it will be load on the CE1. So we address these challenges using the EVPN route type 4. So let us see how exactly it will help us. So if you see here, we have configured EVI 100 and ESI. So EVI, you can say that EVPN virtual instance, means you can say that is the kind of VRF, layer to VRF you can say. And the ESI is Ethernet Segment Identifier, that is the interface which is connected between the PE and CE routers. So you need to keep the ESI same both on the PE1 and PE2, because both you are connected to the same CE routers. So you need to maintain that ESI. But for single homing routers, ESI is not required. By default it will be 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0 So once you commit those EVI configuration, the route type 1, 3 and 4 will be generated by multi-homing routers, and single homing will generate only the type 3, that is multicast, inclusive multicast label. So if you see here, frame send, bump traffic sent by the PE1 will be forwarded towards the PE3 and PE2. So PE3 will attach the multicast label sent by the PE3. So we will discuss the type 3, which is inclusive multicast, in detail in upcoming slides. So for any bump traffic, the router will attach the label which is received by remote PE. So let us say that PE1 will attach the L3 label, that is multicast 3 label, and then top will be transport label, and it will forward to the PE3. And PE1 will forward the same. He will attach the multicast label received from PE2 and the transport label, and he will forward it to the PE2. But as we saw in the VPLS scenario, it is going to send it back towards the CE. But here, using the route type 4, that is we called as the Ethernet segment route for DF selection. So once they exchange the route type 4, so designated forwarder election will happen between them, between multi-homing routers, between PE1 and PE2, and they will decide that who is going to forward the bump traffic towards the CE1. So here we have configured the EVI 100. So for even EVIs, the lowest router ID will be the DF, and for the odd EVI, highest router ID will be DF. So in our case scenario, PE1 will become the DF, and he will forward that frame towards the PE1, and PE1 will send it that frame towards the PE2, and PE2 will say that okay, he is the non-designated forward, so he is not permitted to send that traffic back to the CE1. But keep in mind that is only for the bump traffic. Suppose if we receive any unicast traffic from PE1, he is okay to forward. But if we received any bump traffic from PE3 as well, PE2 is going to block that one. So remember that type 4 is for only bump traffic, not for the unicast. So in earlier scenario, we saw that the bump traffic arrived on the designated forwarder routers, and then non-designated forwarder routers will block that one. But we know that in the multi-homing scenario, we are using the MC lag here. So CE1 will have lag configured on his side, so he can send the bump traffic on any port. So let us see that bump traffic received on the non-DF. So how it is going to react. So EVPN solves that challenge using the Ethernet segment Ethernet auto discovery route type, that is route type 1. So in the route type 1 we have two route type, one is ES-EAD and one is EVI-EAD. So ES-EAD is generally used for the split horizon label. So PE1 and PE2 will exchange ES-EAD with each other. So it will have the ES information and their router ID information, so that they can forward the packet towards each other. And PE2 is single homing routers, so he will simply going to discard that type 1A, but EVI-EAD he is going to execute. That is for aliasing, that we will discuss in the further slides. So they will generate the type 1, and once the bump frame received on the P2, he is going, if he wants to forward it towards P1, he will attach that split horizon label which he has received from P1, and he will attach the transport label on the top, and he will send it to the P1. P1 will say that okay, he is the owner of that split horizon label for the same ESI, and he is going to simply discard that bump traffic which he has received from the PE2. But if PE2 follows that bump traffic towards PE3, he will attach that multicast inclusive label towards the PE3, and he will forward towards the PE3. PE3 will accept that label. For PE3 there is no issue. Next challenge with the VPLS is the unstable forwarding table. So let's say in this scenario, CE1 is sending traffic over one, because it is lag on the CE1 side, so it can send it bump frame on any ports. So let's say that one time it is arrived on the P1 and second time it is arrived on the P2. So both are going to forward it to the P3, and P3 will be in the confusion state, because once it is receiving from P1, he will learn that based on the source MAC address, he will put that MAC address in the MAC table, and after few minutes again he will receive few bump packets or any other packet, any other frame from the PE2. So he will again update the MAC address table pointing towards the PE2. So this MAC will continuously flap will happen continuously in the network. So it's difficult for PE through to PE3 to figure out where to send the traffic exactly. So EVPN address that challenge using the EVI EAD, that is EVI Ethernet Auto Discovery, that will advertise the EVI label. So that will be that label will be generated per EVI basis. So in case of multi-homing, each router will generate the type 1. P1 and P2 will generate the type 1 routes, and P3 will just keep that route with him, that is aliasing route. And once suppose any bump or any frame received from C1, P1 will learn that MAC address based on the data plane learning. He will generate the route type and he will send that MAC address towards the PE3. And once he generates the route type 1 or 2 towards the PE3, he will send that bump traffic using the multicast label towards the PE2 and PE3. So once PE3 received that one, he will say that okay, it has received from particular ESI. So he will try to add that entry in the routing table. But while doing the lookup, he will have hierarchical fib. So if you see that if he needs to reach that particular MAC, he will point it towards the ESI of that particular multi-homing routers, and then that ESI will point towards the P1 and P2. So in this scenario, it is doing kind of load balancing here. So that MAC flapping issue, whatever which faced in the VPLS, it got resolved using the EVI EAD route type 1. So this is that route type 2 advertised by the P2 routers. So here you can see the MAC address and the label value, which he will forward it towards the P3, and based on that label value P3 will forward it traffic towards the P2. So we discussed earlier that we use the type 3 here as well, that is for the inclusive multicast. So whenever you received any bump frame, the P routers will attach the multicast label and then transport label and will send it towards that particular remote P router from where he learned that multicast label. So in this scenario, let us say that P1 is sending the L1 label, multicast label in the network, P2 is sending the L2 multicast label, and P3 is sending the L3 label. So what will happen that once bump frame received from the C1, P1 will attach L3 for P3 and L2 for P2, and top label will be the transport label. Transport label, and he will send it to the particular P routers. So as we see in the DF and non-DF scenario, P2 will simply discard, going to drop that packet. So in the EVPN scenario, we are trying to avoid the broadcast. To simplify the network operation, we use the multicast here. Only that is for the broadcast traffic. For unicast traffic, we will have the label generated by the type 2 route type. We will use that for the unicast traffic. And one of the biggest advantage of the EVPN is the faster convergence, because generally we use here BGP for advertising the MAC routes. So this could result in a slow convergence in the large scale environment based on the number of MACs. So you can see that if you are using this in the data center site, so you can imagine how many MACs will be there. To combat this slow convergence, a level of indirection is introduced. So let us see that if a link between C1 and PE2 failed, so PE2 will generate the withdrawn message for type 1, that is EVI-EAD, which we discussed earlier for the aliasing. So he will withdraw that message, and once PE3 received that message, he is going to simply remove that PE2 entry from his hierarchical FIB table. Make a note here, he is going to simply remove that entry. He is not going to update each and every MAC table. So you can imagine if we have 4000 MAC entries, that will be point towards the ESI. So from the ESI entry, he is going to simply remove the PE2. He don't need to update each and every MAC. So it's become very scalable here. But if we talk about the VPLS scenario, in that scenario you need, in case of failure, you need to update each and every MAC entry. So that's not the scalable solution. And last but not least is data plane MAC learning. So if we learn using the data plane, there is no scalability, no ECMP, and it's a slow convergence. But if we use the BGP for control plane learning, that we called as the BGP MAC routing as well, or layer 2 routing, which will have all the features which routing has, like equal cost multipath. So between the C and P it will be still in the data plane, but between P it's become the control plane using the MPBGP. So as we know earlier that BGP control plane has many advantages like scalability, flexibility, just like whatever we do in the IP routing, so it helps us to do the MAC routing as well. I hope you like this session and thank you very much.